Section 1.4 is collecting sample data. In this section, we're told that if sample data are not collected in an appropriate way, then the data may be so completely useless that no amount of statistical torturing can salvage them. The method that we use to collect data influences the quality of the statistical analysis. In this section, we're going to be looking at different ways of collecting data, what they're called, and once again, this is focusing on the vocabulary in this section. We're interested in coming up with what's called a simple random sample. In a simple random sample, every sample of size n has an equally likely chance of being selected. Now, when you're talking about collecting data, there are two different types of studies in which we collect data. The first one is an observational study where we actually provide no treatment. We're just observing what happens to somebody. And the second one is an experiment. In an experiment, we actually do provide a treatment. So, for example, let's say that we wanted to observe the effects of some disease on the human body. So we take pictures of subjects over time and watch how they degenerate over time. And all we're doing is taking pictures. That would be an example of an observational study. But if we wanted to check and see a potential cure, and we give the group of subjects medicine to see if it affects them, and we still take pictures of them, that's no longer an observational study. That then becomes an experiment because you're giving them a treatment. You're interacting with the subject in more than just an observational capacity. You're actually doing something to them to either improve or their situation. So in these two scenarios here, what I want you to do is identify the source of the data as either observational or experiments. The first one says the Pew Research Center surveyed 2,252 adults and found that 59% of them go online wirelessly. The second one says, in the largest public health experiment ever conducted, 200,745 children were given the Salk vaccine, while another 201,229 children were given a placebo. Which one of these is observational and which one is experimental? The first one is observational. The second one then would be experimental. Do y'all know who Jonas Salk is or what he invented? Polio vaccine. It's a big deal. A simple random sample as opposed to just a random sample. A simple random sample is where a sample of n subjects, n just being any number, is selected in such a way that every possible sample of the same size n has the same chance of being chosen. In a plain old random sample, everybody just has to have an equally likely chance of being chosen, but here we're saying every possible sample of the same size has to have the same chance of being chosen. So for example, suppose I have, and this is the example they use in the book, if we have 6 people in the room, suppose I have 3 males and 3 females in the room, that's 6 people. And I want to do an experiment or select a random sample so that I select only 3 people in the room. And I flip a coin. If the coin lands on heads, I get all the males. If the coin lands on tails, I get all the females. That would be a sample of size 3, but does everybody have the same chance of being chosen in every group of size 3? No. That would be an example of a random sample where every person has an equally likely chance of being selected. They have a 50-50 shot at it, but it's not a simple random sample. In order to do a simple random sample so that everybody has the same chance of being chosen, what we could do is write everybody's name on a note card, put all the note cards in a pile, and then draw out 3 names or 3 note cards. Now everybody has the same chance of being selected on any sample of size 3. Every possible combination of people of size 3 is covered, so that would be a simple random sample. So you need to note the difference between a random sample and a simple random sample. In a random sample, everybody has the same chance. You have an equally likely chance of being selected. But in a simple random sample, all possible groupings of the same size have the same chances. It's a subtle yet important difference. In this book, we are going to assume, as we get into actually doing experiments and stuff, doing inferential statistics, we're going to assume that we have simple random samples. It's a stronger assumption. You're not really getting the difference. Okay, 1, 2, 3, 4. There are 4 rows of people in this room. So here's one row, here's another row, here's another row, here's another row. Assuming that every row has the same number of people on it, I could have a deck of cards. And if I draw a heart, this row is selected to do something. If I draw a diamond, this row is selected to do something. If I draw a spade, that row is picked. And if I draw a club, this row is selected. Everybody in the room has an equally likely chance of being selected to do whatever it is I want you to do. And if I pull out a deck of cards, because there's only 4 suits in the deck of cards, every row has an equally likely chance of being selected, which means every person in the room has an equally likely chance of being picked to receive extra credit. And there's 10 seats on a row. What I'm looking at is this is a random sample, but it's not a simple random sample. It's a random sample because each row has the same chance of being selected. But a simple random sample, let's say that there's 13 people on the row. Not every group of size 13 has the same chance of being selected. So only these 13 people will all be selected together, or these 13 people will all be selected together, or these 13 people, or these 13 people. But I couldn't have somebody from this row and this row and this row and this row all be selected. Does that make sense? Because they're sitting on different rows. So not every group of size 13 has the same chance. On a simple random sample, all possible groupings of the same size, in this case 13, have to have the same chance of being selected. Well, it would be impossible to pick somebody from different rows to be in a group of 13 with the way that I have this set up by drawing cards. What would be a fairer way would be to have 2 decks of cards, hand a card out to everybody in the room if there's 52 students, and then I just draw 13 cards out of the second deck. Whoever card matches the 13 cards that I drew out of the second deck, those are the people that are selected to get extra credit now. Now this is a simple random sample because every possible grouping of 13 is possible. Because you could never be in this row, you could never be selected to be part of the 13 with somebody on this row if I just used the rows to divide the class into groups of 13. But if I used the decks of cards and gave everybody out here a card, and then I took another deck of cards, and if I drew your card, you got selected, that's a simple random sample because you could be picked with somebody from this row or this row or this row or your whole row. Does that help? All right, so a random sample. Members of the population are selected in such a way that each individual member in the population has an equally likely chance of being selected. But in the simple random sample, it's not just the individual members, it's the whole group of a certain size. Systematic sampling is just what the name suggests. We go through and systematically select somebody. So like in this situation, it looks like we're selecting every third member here. So here's the first one, second one, third one, they're picked. First one, second one, third one, they're picked. This is how your teacher, your PE teacher in elementary school assigned teams for kickball or whatever, right? They said 1, 2, 3, 4, 1, 2, 3, 4. All the ones go over here. All the twos go over there. That's called systematic sampling. Convenience sampling is just what it sounds like. You just take the most convenient group that's around. So this person wants to do some research on the death penalty. So they just lean out their window and holler at the first person they see walking by. Hey, do you believe in the death penalty? While it's convenient, the results may not be all that good because you probably don't have a truly random sample. First of all, you're restricting yourself geographically. And what happens if you don't have a random sample? You introduce bias, and no amount of statistical torturing can make your data produce valid results. Stratified sampling. Stratified sampling is easy to get confused with the next one, which is cluster sampling. So let me try and explain it. In stratified sampling, we subdivide the population into at least two different subgroups. The most common would be dividing by sex, male versus female. I've also seen situations where we divide by age, like if you're talking about driving or insurance accidents, auto accidents. The insurance companies like to know, well, how do drivers 25 and under compare with drivers from 26 to 46 and then 50, 47 and over. They're using age, not sex, to divide the population into strata. When you subdivide the population into groups, then you take a random sample from each subgroup or stratum. Now I said this one gets confused with cluster sampling, so let's look at cluster sampling. In cluster sampling, we divide the population into sections or clusters and then randomly select some of the clusters and choose all the members from the selected cluster to survey. In stratified, we divide the population according to characteristics and take a random sample from each category. In cluster, we divide the population into different regions and randomly select a region and take everybody from that region. Here we take a random sample from each group and stratified. Here we take a random sample of the groups and take everybody in that group and survey them. We do this a lot with voting precincts. On election night, we divide the region into precincts, and what they'll do is they'll do a cluster sampling and to try and predict who's going to win what. And they say so many % of precincts reporting. What they've done is they've started totaling up all of the precincts. So if we totaled up this precinct, all of the votes here, and all the votes here, we could make a prediction about what's going on with the voting in that region by counting all of the votes in just a few precincts. Eventually every vote's going to get counted, but this is how they get the early results coming in. Multi-stage sampling is where you may have different stages of data gathering for your experiment or your research that you're interested in doing, and you may use a simple random sample for one, and then you want to use a cluster or a stratified sample for another stage once you have your simple random sample. So you can do sampling in stages. So here are all the different methods of sampling that we have. Let's see if we can remember what some of the important characteristics are. Random sample, what identifies that? Individuals all have the same chance of being selected. Systematic sampling, how does that work? Select every, we'll call it kth, because it could be first, second, third, whatever. Does that make sense to you, the kth subject? No? Well, if we go back to our picture right fast, here it would be every third subject. 1, 2, 3, third one selected. 1, 2, 3, you're selected. The K is just a variable that says it could be first, second, third, fourth, fifth, whatever you're interested in doing. Convenience sampling. Easy pick. What is the most convenient? Stratified. Subdivide by characteristics and then what? A random sample within each group. Subdivide by characteristics. That's a good way of putting it. Cluster sampling. Okay, here we subdivide, not necessarily by characteristics, we subdivide a region and then randomly select regions. And we don't just take a random sample from each selected region, we survey everybody in that region. Alright, and then multi-stage just means you can use more than one of these at each stage. I think the ones that get most confused most often are random sample versus simple random sample and stratified versus cluster. So if you can work to understand those. And the book does a good job of explaining it. So really read the book on those sections. They use some good examples. If you can get those straight, I think you'll be in good shape. The next thing we're going to talk about are the types of study. And your book really does a good job. If you will go to types of study, they do a time reference thing here. A cross-sectional study is where data are observed, measured, and collected at one point in time. This is like a snapshot of what's going on at some point in time. We just take a picture of what's going on at this one point in time, whether it's in the past or current or whatever. Retrospective, or a case control study, is where data are collected from the past by going back in time and examining records, looking at interviews, and so on. This is sometimes called data mining. And then a perspective or a longitudinal study is where you follow a cohort of people into the future, and you pick a group that you're interested in doing and studying that some characteristics of, and you follow them into the future, all of the same people, and see what happens to them. So data are collected in the future from groups sharing common factors. One of the examples of perspective studies that we've done is we've started a new method for teaching developmental math, the CAI math. Have y'all heard of that? Computer assisted instruction. Well, we're following a cohort of students that go through, some of our first students, and we're following them as they into the future as they finish their math, and we're seeing how they compare to another cohort of students who didn't take that method of instruction, that just did the traditional lecture class, and see how they do. Do they finish? Do the two groups finish their college level math at the same time or at the same rate of completion? We want to know, is one method better than another? So we find a group of students that all started together and then see how many of them finish at the end of some time frame. Usually 5 years out is about what we do, what we'll study. So this is in the past, retrospective is in the past, perspective is in the future, and cross-sectional is just a snapshot in time. You're not following anybody anywhere. Design of experiments. These are things that you have to consider whenever you are designing experiments. Now remember, I told you this is an introductory course. We go an inch deep and a mile wide. Each one of these topics that are in green here, we can take and develop a whole course around. So you need to understand that. I'm just giving you some basic terminology. We're not going to actually have you guys designing experiments. That goes beyond the scope of this course. But when you do design experiments, there are some things you need to consider, and one of them is randomization. You have to assign subjects to different groups through a process of random selection. Otherwise, you've introduced bias into your research, and we've discussed that. Replication means that the repetition of an experiment must be done on more than one subject. You want to have a large group of subjects to see, is this just something that happened by chance, or does it look like there's really a trend going on? Blinding is what happens not when you poke somebody's eyes out, but blinding is what happens when the person or the subject of the experiment doesn't know if they're getting a treatment or a placebo. A placebo is a medicine that's not really a medicine if you're doing a medical research. A sugar pill. So, for example, my mom used to work in a hospital. She's a nurse, and they had this guy come into the floor where she was working, and it was late, and the doctor did not leave any orders for pain meds, but this guy was in pain. And he kept calling my mom. He was her patient. He kept calling her into the room over and over and over. Please, have you called the doctor? Have they ordered anything? I'm hurting so bad. I need something. Well, my mom kept calling the doctor, and he wouldn't return her call, which sometimes happens. And when you're a nurse on a floor, you can't just give out even an aspirin on your own decision, on your own say-so. You have to have doctor's orders. And this guy was in agony, and she knew he was in agony, but she was helpless. She reached in her pocket, and she had a pack of Tic Tacs. She took a Tic Tac out, she put it in the little paper cup, and handed it to the guy and said, "The doctor called, here's your medicine," gave him some water, he drank it, and within a matter of minutes he was starting to feel better. Does that mean that he was not really in pain? It's a mind thing. There's something called a psychosomatic response. Psycho is mind, somatic or soma is body, and your mind, because it thought it was getting a pain pill, released the endorphins or whatever to alleviate his pain. Now, had she have told him, she could have been in big trouble if somebody would have told him, no, that's really just a Tic Tac. Well, he wouldn't have felt better, too. He'd started hurting all over again. But that's called a placebo effect. And the reason that we blind studies is because we want to counteract that placebo effect. If you think you're getting a treatment, maybe you're going to have a psychosomatic response and your mind will do its thing. We want to offset that. So in a blind study, the subject does not know if they're receiving the treatment or a placebo. In a double-blind study, Neither the patient nor the doctor knows who's receiving a treatment. And the reason for doing that is sometimes if a physician knows that they're giving a patient medicine, if they're in the test group, their body language could project that to the patient. And the patient subconsciously even could pick up on that. Oh, I'm getting the treatment. I should be getting better. The doctor is happy. So in a double-blind study, neither the physician nor the patient know. A third party prepares the medicines, and if it's a shot, then all the shots look the same. Some have medicine, some don't. Only the person preparing the study knows. The doctor doesn't know, the patient doesn't know. And then sometimes another thing that can happen whenever you're designing an experiment is you can have two variables that end up confounding each other. Confounding occurs in an experiment when the experimenter is not able to distinguish between the effects of different factors. For example, suppose I came up with an attendance policy. We've had trouble with low attendance in classes, so I make this really strict attendance policy. You miss one class and I dock 5 points off of your test grade. And then we have a really mild winter in the spring when I implement this policy. Well, attendance is up now, but is attendance up because I implemented this really strict policy, or is attendance up because we just don't have any bad weather? Well, the weather or the policy, those would be confounding variables. Do you see how that works? It could be an unintended consequence of another variable that I did not intend to measure. In summary, there's 3 very important considerations whenever you're designing experiments. The first one is you have to make sure your subjects are random. Use randomization to assign subjects to different groups. Remember, there's no amount of statistical torturing that can compensate for poorly collected data. Randomization is key to that. Number 2, use replication by repeating the experiment on enough subjects so that effects of treatments or other factors can be clearly seen. You want to have a sufficiently large sample size. And later on in the course, we're going to look at some formulas that will help us determine how large does our sample size need to be in order to be large enough. And number 3, control the effects of variables by using such techniques as blinding and a completely randomized experimental design. So whenever you're designing experiments, randomization, replication, and control for confounding are 3 things that you need to keep in mind. Any questions?